Hello everyone. Now it's time to figure out those internal forces. Like, well, we did that. Isn't it with the two force members the same for everything? Well, with those three force, multi-force members, it's not quite as easy. But don't worry about it too much. We'll get through this together. So we're going to be using the method of sections to determine internal forces. Internal, not external. Internal forces in 2D load cases. And then we'll do some examples. So first off, why do we care? Well, we have these beams right here, and they're structural members designed to support these loads. The loads are pressing down on them. So the loads are applied perpendicular to their axis. Now, one question for you might be, well, why is it tapered? Why isn't it just straight across the entire time? Some bridges it is, some it's not. Well, the internal forces are important to this. That's where this is coming from. The internal forces change, and therefore the size of the beam changes. So we're going to learn how to calculate those internal forces so we can tell why the bridge changed its shape there. Okay. Now if we look at this bridge right here, or this column right here, you see that it's wider at the bottom and then gets thinner towards the top. Why do you think that is? Well, it has to do with the internal forces. They change, and therefore the size of that pillar can change. So you have to keep on going. One more time. Now we have a shop crane right here. Now in this particular case, we see we have a little frame that's added around the joint of this thicker frame. Now this is added because of the internal forces. This is a point of a lot of stress and struggle, and if we didn't have this extra frame, it would likely bend and fail. So internal forces, what do I mean? Let me get this all the way up there. Okay. When I say internal forces, I'm saying at a particular point in your beam, in your member, whatever it is, you're going to cut it, and you're going to figure out what the forces are inside of the member. Because there are forces inside this member that are constantly resisting the external forces, keeping it from moving. And you want to know what those are. Because if you don't understand those, you might not realize that at some points in your beam, those forces are enough to cause it to fail. They might be greater inside the beam than they are at the supports. They might not. So you want to know if your beam can actually survive the forces being applied to it. And this is something we really get into if you take my solid mechanics class, which you can take next semester. Plug, 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 plug. Okay, now how do you do this? Well, it's not too terribly difficult. You cut, you make a free body diagram just like with method of sections, and every time you cut, you always add a moment, a shear force, and a normal force. Now, any one of these could be 0, but you go ahead and place all of them, and you have to solve your equilibrium equations to determine what they need to be to maintain equilibrium. Like in this case right here, you can see that there is no other horizontal force, so that would have to be 0. Doesn't work. If we're doing some of the moments, well, there is a moment caused by this 5 kilonewton force, and so that would need to be taken into account right here by moment B. And as for the shear force V, yes, that V stands for shear force. It is pointing down because this 5 kilonewton force is pointing up. Not terribly difficult, but you still need to practice it. So when I cut this beam, you need to realize that just like with other things, when we have two things that are pressing on each other, their forces go in opposite directions. And right here you can see at the end of one beam, the shear force is going down. At the other beam, the shear force is going up. And the moments are turning in opposite direction. It's because when we join them together, they need to all cancel and become 0 because it's all in equilibrium. If they were all pointing in the same direction, it wouldn't be equilibrium. It's just going to be breaking apart magically. And you don't want a beam that just explodes when you touch it. And boom. I wouldn't step on that beam. I wouldn't use that. Okay. So how do we do this? Just like I said before, these are 4 good steps. 1, imaginary cut. You cut it in different places, and you make a free body diagram of that system. You're most likely going to have to do that for the entire system first to get your support reactions, but then you're going to do it for the individual cuts using the method of sections. Then you need to remember that you have a normal force, a shear force, and a moment at the ends of those beams. And at the ends of those beams, you can then solve. You can look at it and say, like, aha, there it is. You can find what the internal forces are. Now, any one of those might be 0. Once you've done that, you're going to apply the equation of equilibrium and solve for these unknown loads. You may have to do this several times because if you have multiple forces acting along a beam, the internal forces will change at each of these points. And the moment will change all along that beam. Okay, so that in mind, it's about time for an example. So I'll stop here for now, and we'll do an example next time. Have a good day. Bye-bye.